Well, now it decided to work. Okay. Didn't give an error this time. All right, so I have decided to go ahead and simplify the project. I originally wanted to do this idea of selective search, but I haven't gotten it to work the way I want it to yet, so I can't expect you guys to be able to do that in the next week and a half or whatever. So we're still going to go ahead and go with the idea of this region proposal. Instead of doing an exhaustive search, of doing the sliding window search, going across and across and across, we're going to use a concept of segmentation. Okay, and so this is an unsupervised training technique, and it's named after Felsenswalb. Okay, and if you go onto the Scikit-Learn's webpage, they have a link to his paper that was back in 2002 or something like that. And essentially, like I said, it's an unsupervised learning technique that sort of identifies possible boundaries in the image and then tries to balance having trying to decide which ones are actually boundaries of things and which ones are not boundaries of things. And it's all rather complicated. It has to do with graph theory and all this stuff, and it's an interesting read if you've got some extra time. But essentially, of course, it's built in, and it is in Scikit-Learn, and it just works, which is really nice, and it's actually very fast. So I've uploaded this example segmentation Python file, and it loads a single frame from that video stream. I went ahead and pulled one of the frames out of it, and you can see it's already done. It's very quick. And so the frame, this is the frame. I picked this because it's got the slippery sign, it's got two of these ahead only signs, and it has the yield sign. And it would be really great if we could eventually come up with a way of doing region proposal that would propose all four of those signs as possible things to be classified. I haven't gotten to that point yet, so that's why I've just simplified down to using this. So essentially what it does is it chooses portions of that image, okay, and it thinks, whatever parts of the image it thinks might possibly be something. Okay, there's no classifier in here. It basically works off of, is there edges, and is the color similar, things sort of like that. Okay, and so for example, you can see it's gotten this sign pretty well. The smaller signs, you don't really see them in there at all. Okay, these guys here. And here is the image, the original image with the lines that it found. Okay, so here, this sign here, it's decided it's part of these trees, and this sign here is part of this region of the sky. Okay, so obviously it didn't do very well at getting them. Now, my original concept, because there are some parameters you can tune. For example, how large of things you want to have. What is the minimum size for something? So there are a couple parameters you can play around with, and one of my ideas was to play around with these parameters, say make these really small. We can run it again, and you'll see that you get lots more boundaries. So here is with a whole bunch more different boundaries. We have lots and lots of little things. So the idea was that in this region here, I need zoom. For example, for these guys, that there might be many different regions, smaller regions that make up like the arrow and the whole larger thing, and that if you were to combine regions, combine these smaller ones together, you could get the bigger one, and it would come up with the sign as a region. Okay, and so the general concept of that works pretty well, and I've gotten it to work solidly to detect at least these two signs. Actually, that way it'll build them together and build it. But I'm still working on that, and like I said, it's not ready for prime time for you guys yet. But that's the idea, is that you do it with lots of small things, and you can be able to build the bigger ones. Okay, but essentially for you guys, you're going to have to go around and mess around with those parameters to get it to work reasonably well for the signs you're trying to get in this whole video stream. Okay, so I would like you to choose a single set of those two input parameters and use them throughout the entire video to determine whether or not you think something is a sign or not. Okay, so let me go and I'll show you real quickly in the code here. It works off of this this function Felsenswalb. That's what actually performs the segmentation. And they also have a function called mark boundaries, which draws those yellow lines. Okay, so essentially what Felsenswalb returns for you here, what I've named seg, is, here we can look in the variable explorer. Okay, it has the same size as the input image, and it's filled with integers. And basically the integers are whichever pixels belong to whichever class. Okay, so np.min of seg is 0. Okay, that's the smallest class, and then np seg.max 110. So apparently with this this set of parameters, there's 110 different regions that it's proposed with this segmentation. Okay, and so essentially this seg is just like your labels. Remember we had that labels function where it took you know, and it gave you every one of these labels had a different number on it, and that's how you told the different regions when you're doing your heat map. So essentially it's returning the same thing as labels. So whatever code you have that works with labels, you probably have some sort of bounding box function that works off of labels to fit bounding boxes for each one of the different labels. You can just reuse that straight up because it's in the same format. Okay. Then to do the mark boundaries, you have to pass to it the image you want to place the boundaries on, and then you pass to it the segmentation. Okay, so this image right here, I passed to it the original frame as the image to draw the lines on, and then I passed it the segmentation, which is what the Felsenswalb returned, and it put them on here. Okay, I also created this image where it used the labels, the segmentation, and put the lines on it. Okay, and you'll notice I had to do some modification of that because the Felsenswalb here returns something the same size image, and it has an integer, and it uses the highest, the largest possible size memory integer, a 64-bit integer. Okay. Now, if you're going to display an image, generally those are uint8s. Okay, unsigned 8-bit integers that allow you to have values between 0 and 255. Okay, and most of the IM shows and I can't remember what is CV, OpenCV's function for drawing. Maybe it is even IM show. Maybe they're both IM show. But generally, the IM show functions, they allow you to pass to it either something as a uint8 with 0 to 255, or it also generally allows you to pass to it a floating point matrix with floating point values between 0 and 1. Okay? And usually you pass it either one and it will work. Okay? I'm not sure if the plot IM show allows you to pass it an int64. I'm not sure. It probably won't, because if you have an int64, then you could have values that are over 255, and I don't think it works well. It may work, but it may not work well. What I know for sure does not work is that if you pass the seg directly to mark boundaries. Mark boundaries is definitely expecting a uint8 or a float between 0 and 1. Now, you can hard code this. You can put in front of here, you can say np.uint8. You can convert that 64-bit integer into an unsigned integer. But if you have more than 256 classes, then you're going to miss out, because it's going to wrap things around and you're going to have one class trying to be multiple classes. So that's not a good idea to hard code the segmentation into an unsigned integer 8 if you're going to end up having more than 256 classes, which you may well have. So instead, what I've done is I've taken my segmentation, which is that int 64, and I've divided it by its maximum value, where the maximum value is going to be 1, but then all the others are going to be integers between floating point numbers between 0 and 1. So I've converted the integer image into a floating point image, and then it works to add the segmentation onto it. Okay? And you'll notice that seg itself is essentially a grayscale image. And then you pass that to mark boundaries, and mark boundaries returns this seg bound, and it is an RGB image. Okay, that's how you end up getting the yellow lines. How you have grayscale of the things that I passed to it, and it copied that grayscale value over to all the RGBs, and then it put the yellow for the boundaries. So it converted the grayscale image that I passed to it into an RGB image that it got returned. Okay, so those are, you may or may not run into those issues depending on how you end up visualizing some of the stuff in the intermediate that you do. In the end, you're going to take, instead of this individual frame you're going to read in, you're going to be using the video piece, and you're going to be reading in the video, and then each frame you're going to be doing the segmentation, and then you're going to take that segmentation and you're going to do the classification on it. So you don't ever need to actually draw the boundaries. You don't ever need to draw the segmentation. I've done that a lot in the work that I've done in here just to visualize things and see how things are going. Okay? So you're going to end up with an image like this guy. Okay? And you're welcome to develop whatever technique you want here. What I did is I went ahead and took all of these, there were 110 of them in this example, and I put bounding boxes, or I put bounding boxes around them. Okay? Then, as a first order of a filter, I didn't just send every one of those bounding boxes to my classifier. That would take a lot of time, and it would also give me more false positives, because there's ways of pruning out some of these bounding boxes that can't be assigned. If it's bigger than a particular size. Okay, so for example, this is about the largest sign. I'm about to pass this sign. It's the largest it can really ever be in my field of view. And you can see here, it has a vertical resolution of less than 200 pixels. Okay, so if it's greater, if either of the width or the height of this proposed bounding box is over 200 pixels, or you could even probably draw that down to smaller, then just don't even consider that bounding box if it's too big. In the same way, this sign here is probably the smallest thing you'll ever be able to detect, and I don't know, what is that? That's 300 to 330, maybe that's 33 or 40 pixels or something like that. So if something's smaller than 30 pixels by 30 pixels, or either one of those two directions are small, you can prune that out. Only things that are reasonable size do you want to keep. Okay? You might also want to do certain things of an aspect ratio. If you get something 5 pixels tall and 100 pixels wide, it's almost certainly not going to be a traffic sign. So you might do something to check is the aspect ratio of the width to the height of that bounding box within close enough to 1 that you would consider it. Okay, I have seen some situations in here where there are traffic signs that are maybe angled toward the car, and as you get closer to them, they get skinnier and skinnier. So some sort of skinny but tall things you might want to keep, but you'll want to play around with this. And the whole idea is you want to reject things that might possibly be false positives before you send them to your classifier. Okay. All right. So you're going to get these is going to give you your region proposal, and you're going to have to play around with these two parameters. Now, the first one, the scale, is a little bit nebulous. I'm not exactly sure what the units are or how that's affected, but in general, the larger that number is, the larger regions you will have in your segmentation. So the smaller you make that, the smaller things that it's more likely to pick up smaller things in your segmentation. Okay, this min size, I'm pretty sure from the tests I've done on this, and it's a shame, I wish they would say in the scikit-learn a little more details about this, but from what I can tell, this is the minimum size in total number of pixels in that segmentation. So if there's any segment, if there's a segmentation that has less than 1,000 contiguous pixels in it, it will not be included in this thing. Okay, so 1,000 pixels is pretty big. That's 100 by 100, right? No. What is square root of 1,000? 100 by 100 is 10,000?
Yeah. Square root of 1,000 is 10.
Okay, so what is the square root of 1,000? Is it square root of 1,000 is 100? It's not, is it? No. So so if that thing, those 1,000 were square, then a 30 by 30, you know, it would not allow anything that's smaller than a 30 by 30, which is reasonable. That's not actually too big. Okay. So I'm pretty certain this one's number of pixels, and you will not get anything smaller than that. Okay. This one's more nebulous, but in general, the bigger it is, in general, the larger things you get in your segmentation. Okay, so you're going to need to mess around with that and figure out what you need for it. Then for loading the video, that's one thing that I didn't. I'd forgotten I need to prepare for you guys. Let me go ahead and pull out some of that out of here. This goes. No, that one doesn't go through the video. Okay, well, maybe I'll need to prepare that for next time. It'd be better if I actually have some code where it gives you loading in the video. What I've used is there's a CV2 video reader and video writer. They're pretty easy to use, but I'll work up an example for that so you have something to go with. You know what, let me go ahead, I'll upload, well, yeah, you don't, yeah, to train your neural network, you don't need that yet. So why don't we focus today on trying to get your neural network going, and I'll work some video stuff out. The one thing I'm not sure is exactly which modules you're going to need for the video stuff. OpenCV already has it in there, but there are some, you may need some extra codecs for the video, and I'm not sure if you run into problems where it's asking you for a codec. I have some of the things that I imported when I made it work, but I'm not sure which one I actually needed because I was trying out the scikit-learn's video reader and the CV2's one, so we'll have to keep an eye on that, that you may need to install some more things. So why don't I go ahead and cut it there and on this stuff with the region proposal, and we'll pull up the description of this project, and we'll get cracking on trying to do the classification. I did upload the pickle files with the training file with the training data, right? Yes. Okay, so you've got that. Okay. I'm sorry. How long should training take? I'm trying to remember. An epic probably took around a couple minutes, maybe, on my machine. And you don't have to run lots of epics. That's one thing that's better with the convolutional neural networks, is that you know, you may only need to run 10 or 20 epics. What's that? It probably will be faster than Project 2. If you really want to get fancy and want it to go fast, and you've got a gaming computer, you can use your GPU to make things a lot faster. But that's a mess. I've not worked very hard, but I've not been able to get that working on my machine yet. So right now it's better maybe just run with your CPU. It's not that terrible. Okay.
Let's not talk about the speed of it when Tim's here.
Okay. Yeah, I don't want to get you too depressed, huh, Tim?
No, other Tim.
Oh, the other Tim. Why? Oh, why? Because he's going to take that as a challenge and go ahead and try and get the GPU running.
I'll spend like 3 hours trying to make it so a little bit fast. Just a little.
Yeah. Well, if you get your GPU running, we're talking like a factor of 10 better. So it's not just a little bit.
He figured out how to do that and was showing me some stuff with it, and he's like, yeah, you just have to know exactly what data type of everything that you're sending it is. Like, it's an N32 or an 8 or what, like,
Yeah. I'm trying to find, I wanted to pull up this example. This is the example of building a convolutional neural network to do the Roomba problem, okay? And you're going to need to do something similar to this. This network is probably smaller than what you will want for this problem. You'll probably want something larger, maybe more convolution layers, perhaps some more dense layers, overall generally bigger. But the idea is pretty much the same. You want to start off with sequential, do some sort of 2D convolution, and you'll remember that you have to input the input shape. You need to tell it what the size of your image is that you're going to send to it. Okay. Then after every convolution layer, you're going to want to have an activation layer. Okay. And pretty much the standard generally is after you have your convolution layer, then you usually do a pooling layer to bring your resolution down. Okay. Then here I have another convolution, another activation, another max pooling. And so I have 2 convolution layers with their activation and their max pooling in there. And then I go ahead and flatten it, and then I have a single hidden layer of 10 nodes, ReLU activation, and then an output with dense of 2 nodes. Okay, because there were 2 outputs in the Roomba problem. Here we have 43 outputs, so your dense output is going to have 43 in it. Okay, and your activation is not going to be linear, but it's going to be softmax because we're doing a multi-class classification problem. Then you're going to have the cross entropy is going to be your categorical cross entropy is going to be your loss function, and then classification categorical. There's a classification, I think it's called categorical classification. That's going to be your metric. Okay, because the cross entropy is not going to tell you what % of them are correct, but there is a metric for categorical classification. It'll tell you what % is correct. Okay, and so you can use this sort of as a basis for you to go ahead and build your convolutional neural network for the problem of the traffic signs. But like I said, you're going to probably going to want to have maybe another convolution layer. You're probably going to want to have more than just 5 filters here and 10 filters here. You'll probably want to have more, and that's something you're going to want to mess around with. We are shooting for errors, in the high 90s. In your training set, you need to get at least 98% correct in your training set. Okay, and I'm expecting at least 90% correct in this test set that you haven't yet seen. Okay, so you're looking to get pretty good, and what's really amazing is you go and look at some of these images. They're not easy. They're small resolution. They're 32 by 32, right? Is that right? They're small resolution. It's not simple to be able to classify all of these, and some of them, they're like speed limit sign of 40, speed limit sign of 20, speed limit sign of, it's quite amazing what you'll be able to do with these. One thing I do also want you to do is to find once you do go through your classification, to have it display the images that were incorrect, so that you can get an idea about which ones were incorrect and what did it think they were. Okay, and it's just a little feedback. I mean, yeah, if you have 98% right, it doesn't really matter which ones are wrong and why they're wrong, because they're mostly all right, but it's a good idea for you to go back and have a look at what they are. Okay? So I guess in terms of submission, that your last named project5.py file, it will load in the training set and predict performance in the training set and display all of the images that are incorrect in the training set, and then I'll just go ahead and change the path of the file name. Instead of looking to the pickle file of the training stuff, I'll go to my test one, and then it will give me performance in the test set and display the images that are incorrect in the test set.
So that can be tested on any other video?
No, this portion, these first portions of the rubric are only on the test set. That's just how well are you classifying those 32 by 32 images. Okay? Then here is where we're going to get we're going to be on the video. You're going to be doing the region proposals in the video, and you're going to save the video of the bounding boxes, like the video that I showed you that I had. So I can show you guys that again. Where is it? This one. So you are going to produce a video like this, where you're going to where it'll go through it and it'll put bounding boxes where it finds things. And you can see I don't think I get that one. This out here, for some reason, that checkered pattern of that building, it really likes to think that's a no passing for trucks sign. But you know, in here, it's successful. I'm not getting very many false negatives. That was a correct classification. I wonder if I can get it to pause exactly on there. It's 38. So that is the right classification. Okay, and so you're going to produce this video from the stream, and it's a shame. I really wish if I can get that region proposal thing working well. I know I'll be able to get more signs, but for right now, what I said, you needed to get at least 4 different signs is part of it. And I'll update the rubric. It's not going to involve any of the selective search, it's a selection search stuff anymore. It's going to end with this video and having at least 4 different signs correct, and minimal false negatives. I decided not to make some sort of numerical, to leave that subjective. We don't want to get very many. You want to try and shoot where that building, you get a ton of them on that building, but that's essentially one false negative. It's always all in that building, and then occasionally I get tree stuff here and there, and that's not so bad, at least to start with. Okay. So,
will you
yes.
upload that video?
Sure. Yeah, I've already uploaded the original, but this is my annotated one, so you can get an idea about what I'm expecting, for the performance of it. So let's go ahead, put project. I have not done that for the 4th project. Maybe I can go ahead and do that now.
I would want to see how mine does.
Right. Let me see. Where is that? That is Roomba images test. Let me zip this up. Yeah. That right. All right. So let's go ahead and work the rest of today on trying to get something working with your convolutional neural network. Okay.